In the previous video, we saw that a one-dimensional monochrome progressive wave has the expression. This wave is monochrome because it has an unique and constant frequency. Of course, not all waves are as simple as this, but from Fourier analysis we know that any absolutely integrable function can be expressed as a linear combination of such exponential or trigonometric functions, so any linear operator retains their properties in both directions. And we will meet and make full use of such operators in the following, so let's not worry about more complicated wave functions and deal with this elementary form. By the end of the 19th century, Maxwell's electrodynamics has already been successful in all cases, but with one exception: a warm body radiation. According to this theory, the radiation should have had mostly high frequencies, so the color of a warm body should have been blue or even ultraviolet, which is obviously not observed experimentally. This major dilemma seemed to overturn everything known in physics, and that is why it was called the ultraviolet catastrophe. Physicists were beginning to feel that the world is not exactly as it seems, and there are certain hidden truths that are beginning to have observable effects. An era of great physical mysteries has begun, partially unrevealed in the following decades, but which still raises many questions. Some hypotheses had to be intuited to answer our various observations. After all, as Conan Doyle said, once you eliminate the impossible, whatever remains, no matter how improbable, must be the truth. Conan Doyle could have been a great scientist, and the Holmes-Watson duality preceded the wave-particle duality. Fighting with the ultraviolet catastrophe, Max Planck observed in 1900 that if he introduces in the calculation an additional hypothesis, a formula is obtained that perfectly predicts the spectral distribution of the thermal radiation, the color of the heated bodies. This hypothesis, apparently forced, says that the energy of light is emitted only in the form of packets, quanta, each having the energy E equals h bar omega. There was no other way to avoid the ultraviolet catastrophe and keep physics alive, and what was first an assumption or even a conjecture slowly became an accepted theory. For more than 2 decades, physics has been in a state of metamorphosis, but then it has become stronger than ever, though changed and more unintelligible. Of course, as a secondary effect, this assumption brought Planck's Nobel Prize. The next step was taken by Albert Einstein, who succeeded in 1905 in explaining the laws of the photoelectric effect by assuming that also the absorption of light is done in quanta, with the energy given by Planck. This brought Einstein's Nobel Prize and many technical applications, including nowadays video equipment and lasers. So I simply can't emphasize enough the importance of this formula. You're looking at it every day. You're looking at it now. All our screens are based on it. With just 3 letters, this formula brought 2 Nobel Prizes, while E equals mc squared brought none. Many subsequent experiments have shown that the energy of light is quantized so that it has both a wave character, clearly demonstrated by Young's experiment, and a corpuscular one. Maxwell was the first to consider that light has also an associated momentum. In the following decades, a formula gradually emerged that was fully confirmed by Compton in 1923, and hence another Nobel Prize. Using the formula P equal h over lambda for the momentum of light quanta, he was able to explain the variation of the wavelength of radiation following the inelastic collision with electrons, the Compton scattering. Immediately, in 1924, de Broglie responded with an even stranger idea, claiming that these characteristics of quanta of light, which is a particle, could be found in any other particle, such as the electron, and these particles could also have a dual character, the well-known corpuscular one and the wave one, with an associated wavelength according to the Compton's formula. Of course, this also brought de Broglie a Nobel Prize. No matter how improbable this assumption was, some scientists agreed with de Broglie, and in the next 2 years the two forms of quantum mechanics appeared: the matrix formulation, Heisenberg, and the wave formulation, Schrödinger, each with an associated Nobel Prize. Moreover, Davison and Germer, in one of their electron scattering experiments in 1925, generated a diffraction pattern with unexpected peaks, which confirmed their wave nature in full qualitative and quantitative concordance with de Broglie, and brought the inevitable Nobel Prize. So, according to de Broglie hypothesis, a particle has the energy and momentum given by these two formulas. Also, assuming that it moves in a positive direction on an axis, its wave character allows the writing of a wave function analogous to the plane wave. In this classic wave formula, we replace the momentum and energy obtained in the previous 2 decades. This is a wave function, describing mathematically a single material particle. But it is a complex function, with a real part and an imaginary one. How can we interpret these parts to tell something about the usual observable quantities, such as energy, position, and momentum? How can we mathematically express these observables? Just taking the real part would omit the imaginary part with its associated information. One way would be to take the module of the wave function, but it will lose all the important information contained in the phase. However, this is a way of interpreting the wave function, but it reveals some strange aspects, as we'll exemplify later, that even today, after almost 100 years, there is a dispute between physicists about it. Another way would be to reveal some characteristic quantities involved by the complex wave function. This was the next theoretical leap based on techniques already known in physics and mathematics, resulting from the study of special phenomena noted for almost 2 centuries. Probably the first phenomena that attracted attention in this direction were the acoustic ones, in which it was observed that some bodies have their own characteristic vibration or resonance frequencies. Some mathematicians have tried to generalize this behavior, and in the 19th century, Hermite demonstrated that certain mathematical entities, called operators, that act on a complex function can generate real values, i.e. exactly the answer to the problem of the observables in quantum mechanics. Let us consider a square n by n matrix A. We may construct an adjoint matrix, A dagger, as a transpose and conjugate of the A matrix. So each element of the adjoint matrix is a conjugate of the initial matrix and the indices are reversed. Now if the adjoint matrix A dagger is equal to A, it is named a self-adjoint or Hermitian matrix. If we multiply such a matrix A with a vector f, we may obtain the same vector f multiplied by a real value v. To demonstrate this, we first transpose both members. Now we multiply at right with f and obtain. On the other hand, if I multiply at left with f dagger, we obtain, if A dagger is equal to A, by comparing the relationships 3 and 4, it results that V is equal to its conjugate. Hence, it is real. Mathematically, it was described by such an equation. A applied to F equals V multiplied with F. The value obtained, V, is characteristic for the respective operator A, and this is why it was later called an eigenvalue. Also, the function f, from which this value was extracted, is characteristic for the operator, and was called an eigenfunction. Such an equation, by which an operator acts on eigenfunctions and generates eigenvalues, is an eigenvalue equation. If you are familiar with operators and eigensystems, you can skip the next minutes of this video. It all started with the matrix calculus and the geometrical interpretation of some matrices multiplication. It's not very straightforward to visualize, but a square matrix may rotate a vector. For example, a vector B in a two-dimensional space is a column matrix with two lines, the vector's components. When you multiply a 2 by 2 matrix A with this vector, you obtain another vector C, generally with a different direction and length. A dot B equals C. So these are the matrices, the original vector B, the operator matrix, and the result C. Now let's construct these vectors from origin to the tip of the vector. This is B vector, and now C vector. Let's construct a graphical object consisting of an arrow from origin to the tip of the vector. This is the first vector. Let's show it. And the second vector, C. Let's show both of them. You may see there is an angle between them. Let's identify the first one with red, the second one with blue. Now they're a little out of the scale, so we'll use a plot range a little larger than the vectors. Let's make a frame for them. Now we can see that the blue vector obtained is rotated by a certain angle. Let's show the direction of the first vector as a dashed line from -2, the length of the vector, to +2, and we can see that after applying the operator, the angle changes. But for a certain matrix, we may find sometimes a vector that is almost in the same direction. This is an eigenvector for the 2 by 2 matrix A. Now let's try to manipulate these vectors First, we'll manipulate a component of b, b1, between -1 and 1, and the other component would be obtained from the condition that the norm is 1. So our vector is now b1 and b2, and we'll modify the arrow specifications from origin to this vector. And also for C, the dashed line will be expressed in terms of B, and we try to manipulate this vector and see that the blue one is rotated by a certain angle. We may also establish the eigenvalue, because it is a norm of C, as the norm of B is 1. So here we have an eigenvector, and here there is another one. Mathematica knows how to calculate an eigensystem. This is an eigenvalue and the eigenvector. And this is other eigenvalue and another eigenvector. So we have this wave function associated with the particle. How can we extract an observable from this using the eigensystem method? We need to find operators for that observable. First, let's find a momentum operator. Deriving the wave function in relation to x, we obtain, which can be written This is obviously an equation with eigenvalues in which the operator h over e, or the derivative of c in relation to x, gives us an eigenvalue for p multiplied by c. One may conclude that the momentum operator is h over e, or the derivative in relation to x. To show that this is an operator, we will put a hat on it. Now let's find the energy operator. By deriving the wave function in relation to time, we obtain minus e over h bar e, or psi, which can be written as an eigenvalue equation. We may conclude that the energy operator is IH bar, or the derivative in relation to time. On the other hand, we know the classical expression for the total energy. The kinetic energy is squared over 2m plus the potential energy. Let's use here the momentum operator that we found before, and we may derive another operator for the energy. Now, Schrödinger's Nobel Prize idea was just this: put a hat on E. Using the new energy operator, Schrödinger obtained his famous equation. We all know what happened after this. Everything worked perfectly, and our present technology is based on this equation, which predicted with great accuracy everything that we wanted to calculate. Quantum theory became the most successful scientific theory of all time.